This episode of Gauging Quality is sponsored by PQ Systems, developer of GaugePack, the original gauge and calibration management software. For more information, visit pqsystems.com.
Welcome to Gauging Quality, a live video program that allows you to learn and ask questions about measurement and calibration. I'm your host, Dirk Ducharme.
And I'm Craig Howell from CPM Labs in Rancho Cordova, California.
And today's episode is brought to you by PQ Systems. PQ Systems offers gauge management and SPC software and training to help customers demonstrate proof of quality in products and processes. For more information, visit www.pqsystems.com or click that banner just underneath the player page there. So, Craig, we are looking at a lot of equipment today, and actually answering some users' questions as well.
That's right. We're going to cover a number of topics, probably 5 of them in particular. We're going to be starting with measuring threads with the 3-wire method, measuring over the wires. Next, we're going to talk about dial indicators. The front end of the dial test indicator is called the contact point. And we're going to talk about the effects of different lengths, different ball diameters, different qualities of contact points.
Some misconceptions.
That's true.
And some places where things can go wrong.
So some things to keep in mind when you're purchasing new ones.
Okay.
Then we're going to talk about measuring flatness a couple different times in this show. One of them is going to be optically, using an optical flat over, in this case, micrometer anvils and spindles, just to see how flat they are. They have a spec. They have to be flat within a certain spec, and this is a good way to do it.
Is that something many people know about, the flatness of the anvil on their micrometer?
They should know about it, because some people think if they have a set of gauge blocks, they calibrate their own mics. They're doing part of the job. A very important part, but they're only doing part. You have to measure the flatness.
Okay.
So yes, they should know about that. We're also going to cover inside micrometers. There's a lot of technique involved with that, and some misconceptions on that too.
Okay. And then this is great. We actually got a question from a user, one of our viewers not too long ago, related to flatness measurement.
Measuring flatness using the 3-point method, 3 jack screws, and some misconceptions that they had, and somebody showed him a better way to do it. He can't find that guy, so we're going to be that guy.
You're going to show him the way to do it?
We're going to show him the way.
Before we get started on the thread gauge, just so you know, you can ask questions live during the show. Send your questions to techno-live@qualitydigest.com. I believe it's down there below your screen. Techno-live@qualitydigest.com. We will try to get to your questions during the show. In fact, one already came in. We'll get to that at the end of the show. Just send them to us, and when we have time, we'll get to them. We'll answer them live. And if we don't get to your question, we still have your email, because you're emailing it to us at techno-live@qualitydigest.com, and we will send that on to Craig, and he will try to answer your question offline if we don't get to it.
I'll be glad to.
All right. Thread measurement.
So we're going to start off measuring threads. The pitch diameter is marked on the thread handle, and that is not on the outside of the thread. It's down inside the V. It's at a very known area called the pitch line. And we measured with 3 wires. They're very precision wires. We're going to be using Van Kuren wires in this case.
And no, this is if you don't have to do like a go-no-go gauge is just a very a go-no-go thread gauge is just a very coarse way of doing this, right? This is when you actually need to know what the real pitch diameter is?
This is to check those go and no-go gauges, to verify that they're in tolerance, because they wear out. As they thread the go gauge in and out, it wears, it turns from a bright, shiny surface to a dull gray. And there's a certain amount of wear they're allowed. When they get beyond that point, they pop out, they're throwaway.
So this is actually a calibration technique we're looking at.
It's a calibration, but a lot of people will also measure over wires if they don't have, let's say, a ring gauge of the certain size they're trying to measure an outside thread, an external thread. So they'll put the 3 wires in. So we're going to set up, I'm going to set up on my supermicrometer here, and probably will want to go to this area.
Okay.
What I've got is I have my thread gauge, and I've got the 2 wires on one side.
Yeah, if we can go to the microscope camera there. There we go.
There we go. 2 wires on this side, and I have the 1 wire on this side, and they're staggered, so it encompasses 1 full thread, one full revolution.
Can you wiggle those a little bit? Maybe they can...
I will.
Just in case they can't see the wires there.
There's the 2 wires on this side.
Okay.
Whoops. Upside down. Actually, the 2 wires are on this side.
Okay, we see them. Okay.
All right.
On the left side of your screen, so you got your 2 wires. Okay.
So then I'm going to rock the gauge back and forth and look on my indicator for the lowest reading. Then I'm going to zero it out with my super micrometer.
Okay, so you're going to be looking, we're going to be watching this analog display up here, right?
Right. Let me get down here and get this set up. with the 3 wires. There, that's good. Now I'm going to be watching my display looking for the lowest reading. And when I find the lowest reading, right about there.
Now, what is the purpose for rocking this back and forth?
If I'm cockeyed, since I have 2 on one side and 1 on the other, I have to be perfectly vertical on that pitch line. So now I'm going to zero my micrometer. And there, now as I rock it, it comes back down to 0. Now I would read off the micrometer. Now since we are measuring over wires, back at the normal camera here, since we're measuring over the wires, we're measuring the outside of them. We'll have to subtract, there's a little compensation number on the tube. I would subtract that, and then we'd read the pitch, write it down, and see if it compares with what the thread is supposed to be.
Okay, so you rocked this, you put your thread wires in.
Yes.
You rock this back and forth till you get your smallest reading.
Then I zero the display.
Then you zero it with your mic. Okay.
Then I read the numbers, do the math, and I can compare if this thread is in tolerance or if it's worn out.
Okay.
So that's how we measure threads over wires in a micrometer. There are also thread pitch micrometers. There's a number of ways you can measure external threads. This is the most accurate, but it involves some technique. You have to not drop the wires.
And this is, I should say, I've seen you do this with much finer threads. I mean, these are fairly large wires. We've obviously got a, what is that, an inch,
12.
Inch and a half? Or
This actually was a 2-inch 12,
okay.
12 threads per inch. When you get down in the 48 threads per inch, they get very thin. When you get down in the 72 and 80 threads per inch, it's about the size of a hair.
Don't drink coffee before you're...
Don't drop them. So that's how we do that. Let's go ahead and maybe set up for the next thing for dial indicators.
Okay, and there was something you wanted to point out about different types of threads, was that?
Yes, thread plug gauges always will have the letter A after the designation. It'll be an 832 I'm sorry, thread plug gauge should have the letter B. It'll be an 832-2B-3B. It'll always have the letter B, except for one type of thread gauge, which is the one I happen to bring. It's made for setting rings. It's not made for checking the product. If you ever have a thread plug gauge on the floor and you're checking holes with it, if the letter A is on that thread gauge, it's not to be used. That's for setting rings. That's a special purpose.
Okay.
So that's how you can always tell if you're reading a blueprint or a spec and you're not sure if they're talking about a plug or a ring. If it says the letter B, it's a plug gauge.
And what's the danger, the problem of having an A out there when you should be using a B?
The B is set to the right parameters of what you're looking for on a thread, 832, a quarter 20.
Okay.
The A is made to set up a ring gauge. It's a whole different spec. It's
okay.
a whole different size. If your A thread gauge fits in, you probably have a problem.
Okay.
It should not.
All right.
So I'm going to go ahead and remove these.
Okay, so now we're getting set up for our next...
for indicators.
Okay, so now we're going to look at dial indicators, and Craig and I need to switch some equipment around here on our surface plate. So you need the stand, right?
Yes, I'll need the stand.
Oh, gosh. That's heavy.
And the height master.
And the height master. All right. There we go.
Great.
Sure where you want all that?
Yeah, I'll plop that right over here.
And I guess we can change places now, I think.
Yeah.
All right.
And you'll have to help me set up underneath the
Sure, no problem.
Get this over here. There we go.
And I believe, see, you wanted this, I think we wanted our little microscope cam aimed over here. All right. Move that up a little bit.
All right.
That's our microscope camera. And
there we go. Now we're there.
we will adjust this one as we need.
So all right.
So we're going to be looking at...
this dial test indicator, and we're going to be looking at the contact points that thread into the front end of them in particular. This is our dial test indicator.
Okay, actually, let's go to the overhead cam here. Get this...
Perfect.
All right, that's our dial test indicator, all right?
Yep. And let me move these contact points here so you'll be able to see them. I have 3 different length contact points. The question always comes up, and a lot of people will ask me this. I want to use a different ball diameter. The ball's too fat, it won't fit in the right area for me. Is that going to change anything? The answer is the ball diameter is irrelevant. The ball diameter is up to the user. The length is what determines the accuracy of the indicator, and each indicator is made for one length only. You can't interchange lengths and get a correct measurement.
So you're saying the ball itself, you could have a big old ball, but as long as it's on the right size
Length.
you're
good.
The ball diameter doesn't matter.
Right. The problem is these all share common threads in a lot of cases. You can take this indicator contact point out and put in the short one, or you might have to get way deep in a hole. Some people are tempted to put in a long one. They really need to switch indicators. These are set up, and I'll show you the difference between lengths, what happens.
Okay.
So now I'm going to get over onto this setup, and this is what we're going to be using. And what I will do is I'm going to set this up. There we go.
And this is the correct length for this dial indicator?
This is the right one.
Okay.
I'm going to move this gauge block stack up 30 thousandths because that's one revolution of this indicator, and we'll see what it reads.
Okay.
There, so I moved it up 30 and it rotated exactly one revolution, just like you would hope it would.
Let me,
this is a good indicator.
let me see if I can get a shot of what you're talking about there.
All right. Right here.
Oh, there we go. All right. So now we're on your indicator.
Okay. So I'm going to rotate and I'm going to move that needle 30 thousandths. I'm raising my gauge block stack 30 thousandths, and it should read within one division, and it does. It's reading very close to one division.
Okay, so just to reiterate what we just did, you moved your precision
Gauge block stack.
gauge block stack exactly 30
thousandths.
30 thousandths, and sure enough, the dial indicator indicated
It read 30.
it read 30. Okay.
So let's go back to 0 here and put in the wrong length tip, because this person had to measure inside a deep hole. They used a real long tip.
So they said, hey, I got a long tip. I'll just put this puppy in there.
It fits. It threads in.
Yeah.
So now I'm going to go back and we're again going to measure that same 30 thousandths of an inch. Let me get this thing threaded in here correctly.
Okay, so you're going to zero this out.
Yep. And I'm going to move it 30 thousandths. I've just raised the gauge block stack 30 thousandths. Instead of reading 30, it reads around 12.
Ah, okay.
That's the difference.
So you move the gauge block stack 30.
30 thousandths, and it only read 12.
And that's with putting a tip that's longer than it should be.
That's too long.
For that dial indicator.
It's just over 13 thousandths, so it's way off. Now I'm going to go the opposite direction and put one in that's way too short, which some people will get them in and they'll be way too short. And this will go the other way around. This one, if I moved it 30 thousandths, it's going to peg the needle. So I'm not going to move it 30. I'm only going to move it 20, just so we don't damage anything internally on this indicator. All right. So I start out at 0. I'm going to move it 20 thousandths. There, I've just moved it 20, and it reads 25, 26. It reads 26
so
thousandths.
you move the gauge stack 20, and now it's reading longer or higher than what you actually moved. It's measuring, what'd you say, 26?
26. Okay. So you can see length is the critical feature in this.
Now, most, here I think to me is the crux of the matter, is that some people would say, well, gee, I mean, I know not to use, the wrong size tip in a dial indicator, but you're saying sometimes people are simply buy inexpensive tips rather than spending $20 for a tip. They might spend, well, I can get a tip for $8, and it's the right size. It's what difference does it make?
And that's true. And what happens in that case is when we calibrate them, the tolerance is plus or minus 1 division. With the wrong length tip, even 3, 4, 5 thousandths difference.
And by wrong length, we mean something that's it's a cheap tip, so it's not precisely the right length, right?
It's inexpensive. They didn't spend a lot of time measuring them. They might have used lesser material, cheaper material, but it's the wrong length, just a little bit, 4 or 5 thousandths of an inch. It will be off 2 or 3 divisions, and we can't get it to come in. We'll pull that tip off and say you need to get the correct length, even though they'll swear up and down they just bought a new one. It was 3 for $1.
Come on.
They got 2 left. The point I did want to make, though, is that, do we go to the overhead cam here first?
Yeah, and go back to the overhead cam.
That you can use, within the same length, you can use different ball diameters. Those will all measure the same. They'll fit into different areas, would be the advantage of using a different size ball.
Right.
Small ball, you can get into very thin areas. Large ball, it's a very stable measurement.
Okay.
So it's the ball diameter is interchangeable. Length is not.
Okay. So the key is make sure you're using the right length.
The right length.
For the dial indicator, and make sure you're using good tips.
A good quality tip.
Good quality.
Another thing that can happen with the lesser, the more inexpensive ones, they'll use a cheaper quality of steel, and the ball itself has to be round. That's how it's designed, is that as it moves, being round, it's staying tangent. They will flatten with wear, especially if they're on a machine that's measuring up and down. They'll eventually wear, and you'll get a flat spot. It'll measure erratic. It won't move, and then it'll jump. Sometimes the wear's on the bottom, sometimes on the top. Depends how it's used.
Right.
The better quality, the balls will hold up. They're usually carbide. You can get them in ruby. You can get them in all different materials from a good contact point maker.
And part of your job in a calibration lab is to actually inspect the
Yes.
under like a microscope or something like that?
We usually will. If we're on site in the field, we might use a handheld magnifier, but you'll see it's bright and shiny when they're good, and as they wear, it starts getting dull. Then you start noticing a flat spot. Eventually it looks like a half a moon.
And even a little bit of a flat spot is going to make a difference on the accuracy of your reading. Okay.
That's why they're interchangeable. That's why they thread out. You can buy a new one and replace it.
Okay.
So that took care of dial indicator tips.
And while we're getting set up for the optical flatness, which is what we're doing next, right?
Yes,
optical
it
flatness.
is.
Okay. Just remember, if you've got any questions, it could be related to what Craig has been talking about, or what he's going to talk about, or it could be something completely unrelated, but measurement-oriented, dimensionally measurement-oriented. Go ahead and send your questions to us at techno-live@qualitydigest.com, and we will get to them towards the end of the show, or if it happens to be related to a segment, Christopher will say something in my ear, and we'll interrupt that segment and get that question in related to that as well. You need your light.
I need my monochromatic light.
Okay, monochromatic light.
Let me explain a little bit about what we're going to do here. We're going to measure flatness optically. This light is a very specific wavelength. It's a helium bulb, and the wavelength of this light is 23 millionths of an inch. What the light's going to do is go down through the optical flat. We have a double-sided optical flat that we brought. We brought optical parallels. These are a little easier to handle here under the light, so I'm going to set up with them. What happens is the light will go through, the helium light will go through. This optical flat will be in contact with the surface, and it'll bounce back and interfere with itself and create light and dark bands. You're going to see light and dark bands. It's not the amount of bands that we're concerned with, it's their curvature.
And I think we've got a little...
I have a little graph here that might explain. These are the ones we want to...
Okay, if we can show on the... go to the overhead cam there.
There we go.
So these are the light
these.
bands which you're talking about. Oh, this way?
Yes, the curve. It's the curvature of those bands. It's not necessarily the quantity. What we will do, I'll show you an example. We're going to go ahead, and this is going to be a very, very good quality. You're going to have to hold the camera.
Okay, so we're going to go to our little microscope cam here, so we can hopefully zoom in on this for you. So stand by while I
move your hand.
Try to aim this. Keep my hand out of Craig's eyes.
Go.
And okay,
so I don't know if you can see that. If you're
almost
seeing those
focus
interference
here.
bands, you just about are. Yeah. There's quite a few of them, but they're straight as an arrow. There. They just have a very little curvature. If you were to draw a straight line, like with a piece of thread or a ruler, between the start of one light band and the end of that same one, nothing crosses over it. You see how flat that is? They're straight. I'm going to put in a bad one. I don't think we'll get any reading at all. If we do, it's going to be curved like a beach ball. No, we're not getting any reading. This is, you can see how shiny this one was. That one is just very, very shiny, very flat. This one is dull and worn. You can see the wear on it. It won't even reflect light bands.
Okay.
So now I'll just draw a little example.
Yeah, draw just, and you can probably do it right here underneath the.
You give me set up and I'll draw.
Yeah, why don't you do the overhead cam here?
All right.
Yeah.
Got it. So I'm going to draw. I wasn't able to find one that was bad just exactly the way we wanted it to be. And if we had one that had worn, those bands would be curved. Remember, our bands were straight, parallel to each other. But as they wear, you'll get a curved pattern. And what we're going to do, to check the flatness, we're going to count how many light bands pass over. Here's the start of that band, follow it through to the other end.
So you're going to take one band.
One band and draw a straight line through it. Well, as straight as I can draw.
And you're going to try to do this typically just kind of visually?
Or some people tape thread up so they can get their head over the thread and make it pass. So what we've got, this is the light band we started with. So from here to here is one light band, two light bands, three light bands, and a little. Now each light band is 12 millionths of an inch. So 1, 2, 3 would be 36 millionths of an inch, and let's call that a quarter. So if a half is 6, a quarter would be 3. This would be about 39 millionths of an inch. A typical 1-inch OD micrometer is allowed 50 millionths. So you can get, we usually, if it's about 3.5 or 4, we'd recommend it getting resurfaced. They do resurface them.
Okay.
So that's how you can measure optically.
Ah, okay. So typically what you would do, and this is something that, this looks relatively inexpensive. I mean, the light source is probably relatively inexpensive, no?
The initial investment, nothing in calibration is
okay, all right. But if you were going to be doing, I guess my point is, if you were going to be doing your own in-house calibration of micrometers as opposed to sending them out to somebody like you, I mean, you're getting ready to retire, right? I mean, you need to work anymore, right?
It should happen.
If you're going to do your own in-house calibration, then obviously what you're saying is the flatness of the anvils are really a critical part of that.
They really are. And then the one other thing, these are called optical parallels also. I'm going to go underneath the light.
Oh, okay.
Is where I'm going to be heading. And these little flaps are parallel top and bottom. In this case now, we're
back to our microscope.
Yep, and we're going to count the bands this time. There we go. We're going to count the bands, and I see 1, 2, 3. Yeah, I'm seeing 1, 2, 3, possibly 4. I'm looking at 3. 3 light bands. Now we're going to turn it over and count the bands on the other side. You're going to have to, here, I can actually come to you. And we've got about 1, 2, 3, 4, 5, 6.
Oops, well,
so we had
here.
We had 3 on one side and 6 on the other.
Hold on a second, I'm trying to get in.
There we go. Yeah, you're showing it. There are 6 bands there, 3 on the other side. Now we will take the quantity. 6 minus 3 is 3 light bands, so the parallelism of this, again, is 12 per light band. So now out of parallel is 36 millionths, 3 light bands. This is a little different way of using it.
So what you did is you used a different optical flat, or you flipped it over?
It's actually now in contact with both surfaces.
Oh, I get it.
Originally I was in contact with one. Now we're in both, so we would count them. There's 3 on one, 6 on the other. The difference is 3.
I get it. So the three was on one anvil,
yes.
The 6 was on the other anvil.
On the other anvil, without changing anything, just flipping it over. That will show optically how parallel or unparallel it is.
Yeah, okay. And they need to be within...
Again, there's a spec for that.
Okay.
Now this only checks the anvil at one place. Well, the set comes with 2. It comes with 2, and one's a little thicker than the other, and it's exactly half a barrel rotation as the other. So you're checking if these were both worn.
Oh, you're rotating
but parallel.
You're rotating at 90 degrees.
You're rotating at 90.
Okay.
So now it will show up.
Okay.
So that's the difference on these. These are still optical flats, but both ends are parallel.
Okay.
The large one, each end is flat, but there's no guarantee they're parallel.
Okay.
So that's optically how we measure flatness.
Okay. Yeah, you guys got all the toys. So what are we doing? Oh, inside micrometer next, right? Or
yep. Inside micrometer.
I think Metrology calls it a tubular inside micrometer.
It is. It's tubular.
And thanks to Mitutoyo for sending us one of these for the sake of a demo. Maybe we can get the, let me get the overhead camera here. Zoom out a little bit. There we go. That's the whole kit.
There's that.
And this is the actual business part, right?
All right. This is a Digimatic model, which is digital, which is just great. You don't have to read the vernier. You can see it when you're down inside a bore, as opposed to if you're trying to read the vernier on the micrometer and you're trying to figure out what and you move it. This, you can see them, the digits. It doesn't take any interpretation.
And also, I should mention, this one actually has, I think they call that a Digimatic output, a digital output. Most modern electronic gauges do have a digital output, and really one of the real advantages of that, aside from being easy to read, is if you're using some sort of gauge calibration software, such as, let's say, PQ Systems Gauge Pack, or any other type of calibration software. One thing that you can do is usually, on most of these, be able to take a measurement directly into the software. So rather than have to read 8.0362 and type in 8.0623, you hit a little button and that measurement goes directly into the into the software. Which
and the software you can do a number of things.
And yeah, exactly. So gauge calibration software is really a good investment, and particularly if you have electronic gauges, just makes it a lot easier to collect your data rather than trying to transcribe it and hopefully not making mistakes when you do that. So
this particular micrometer, the end will unthread.
Yeah, and as it says on the screen, this is an 8-inch to 40-inch tubular inside micrometer.
Your basic length is 8 to 9 inch. The micrometer head will move 1 inch out. But these have interchangeable tubes. It's tubular.
It's tubular, as we say in California, back in the 70s.
So they have 1 inch, 2 inch. This is an 8-inch extension rod or tube.
Okay, so that would add 8 inches onto the 8 inches we have.
So now you're going to be reading from 16 to 17 inch.
Got it.
And again, since it's calibrated and set up with this on, you need to put it back on to finish up. You can't just measure on the end of the extension.
Right.
There. Now you are set up. It will read 8 at this point.
So you're just going to add the length of your extension onto the base 8-inch
and these are marked. So you would add the reading to whatever you're marked. So these are very handy.
And so you just keep stacking up these tubes.
Right. You just keep, one goes over the other one, and one goes over the other one. You keep stacking them up.
Like those little Russian dolls.
So that is the Digimatic. I'm also going to show you, I brought along an older analog model, which starts out at 4-inch. Same idea, but it's analog. I'm going to visually show you the difference. You can see how useful having the Digimatic is.
And so this is just a regular manual one with a vernier
right, you read it just like any other micrometer.
Okay.
But the caps will unscrew, and that's where you add the rods on. But this is the style where you have to read 25 thousandths per revolution, and you have to figure, okay, we've got 157.
Got to put your glasses on. Okay.
Technique on these is all important. That's really what I want to cover, is how you measure. Technique is very important.
And we just happen to have an 8-inch precision piece of
Let me get that.
kitchenware. That's right from my kitchen. We have a precisely made 8-inch saucepan. There we go.
Yes, but I think you want to take this back because you didn't get your money's worth. This one I have to go, they shorted you. I'm going to show you what we do with how you work an inside micrometer. First of all, we're going to rock it back and forth left to right to get the largest diameter.
Okay.
Then we have to pivot it up and down to get the smallest. So there's a ton of technique involved in this. When people don't trust inside micrometers, it's normally not the micrometer. It's the technique. So I'm doing both at the same time. I'm going left and right.
So you're going for the largest?
Largest left and right, and then it'll stop as I try to go up and down, so I have to go smaller on the up and down. There we go. And when you get it just right, it'll just whisper through. You'll just feel it start to contact right there. So your 8-inch pot is measuring a little under, Dirk.
And you're
You're off.
Yes.
So
6/600ths off.
Yes.
It doesn't hold quite.
We couldn't find anything large enough to fit
Yeah,
an 8-inch.
a little hard to find an 8-inch machined part just on the last minute.
And then
yeah.
lift it onto the plate. But the real technique is where the problem comes into play. A lot of people say, well, you know, you can never trust those inside micrometers. They never measure right. You're going to have to measure over the top of them with an OD micrometer. That's a bad move. If they've been calibrated. If they haven't been calibrated, all bets are off anyway. But if they've been calibrated, it takes us a lot of force to adjust these. They don't move.
So you're saying some people will take one of these.
They'll usually be using one of these.
One of those, and they'll measure it with
an OD mic because they don't trust the reading. And before they've been calibrated, I can understand that. But after they've been calibrated, all you're doing is throwing in the tolerance of the OD mic with the tolerance of the ID mic. You've just doubled your tolerance.
Right.
And there are errors you might make in measuring.
In the measuring itself, yeah, exactly.
It's technique. It's the left and right looking for the largest diameter, up and down looking for the smallest. And that's where 90% of the problems come in.
And where typically would you use, I mean, why would you use this instead of like an inside, you know, the regular, like an inside like caliper or a micrometer? You know, why something that you stick down inside?
A good example might be an O-ring groove. The caliper is flat bladed. It's only going to measure the diameter. An O-ring groove is cut down inside of something and it goes inside. These might fit the O-ring groove where your caliper wouldn't.
Oh, so you would
somehow work your arm down in there,
yeah, okay, yeah.
do the thing. Then you have to take the reading down there because you can't really get it out.
Okay. Well, which is actually another advantage of
Digimatic.
Yeah, you can have your little display.
Especially if you have a foot switch and you go down there, you've got the right feel, you tap the button, you don't care what it read. You've already recorded it.
Okay.
So
right.
You do care, but you've already recorded
it. And there's other types too, like the little 3-prong type.
This is a two-point. This is your typical inside micrometer. Then there are the 3-legged ones. All the brands have different names. Mitutoyo calls them whole mic. Brown and Sharp calls them intra mic. They have different names for them. I forget what the different.
But they'll work
ones
basically
are.
the same, right? They kind of got a little three.
Those have usually a knob, and you'll turn something from the top, and 3 legs will expand out.
Okay.
And those are very handy too. There's not quite as much of that feel to it because now it's self-centering. You don't have to worry about finding the largest diameter.
Right,
you still have to worry about are you perpendicular.
Yeah, perpendicular. Yeah.
So that's everything you've needed to know about inside micrometers and the precision holes we measure with it.
Exactly. All right, and now we're going to move on to a question that came in a couple days ago from a reader who really just had was a little confused or wanted some more information on how to measure flatness using a 3 jack screw method, I guess you'd call it, huh, Craig?
Yes, we're going to set up for that. We're going to set up, even though normally for flatness measurement you'd use a higher resolution indicator than what we have. This is a 5/10,000ths of an inch, or 5/10. Usually you would use a 1/10. In our lab we use one that goes to 5 millionths, but that's irrelevant. Let's start out with what we have.
And as Craig's still getting set up here, just remember, if you got any questions related to what you've seen on the show or something else, just feel free to send them to techno-live@qualitydigest.com, and we will get to them here in just a few minutes.
All right, so what we're going to do here is we're going to check flatness. We wanted to check flatness on this part, and this is a very flat plate. It's a toolmaker's flat. So it's flat within about 12 to 20 millionths of an inch. It should show no variation at all on the indicator. What we've done is we've made a bad spot on it. I taped a piece of paper on it to simulate either I wanted something dished, but I couldn't do that to my flat. So I went the other direction because that will represent a bad area on the part.
So if we can go to our overhead camera here.
I'll get this set up.
So what you've done is you have put the jack screws underneath 3 points that you've already just kind of marked on the.
I have, and I've just basically. The thing about flatness is it's a single surface measurement. You don't lay this on the plate. Now you're checking parallelism also. If the part was not parallel, it could be flat as a pan. It could be flat, and you'd still show a reading.
Oh, because Oh, if the
you're
bottom
laying
isn't
on the
parallel
plate.
to the top and you set it on the
Right.
plate. Okay, gotcha.
So the best way to define flatness is to make a plane. And what we're going to do to make a plane, if we get 3 points to read all the same, if we get 3 points to read the same, we'll know that we have a flat plane. So what I'm going to do is adjust these jack screws till they measure the same at all 3 locations. Then we've defined a flat plane, and we'll check all over the rest of the part to see how much it varies. It takes a few times to do this, back and forth, but I'm getting the indicator to read the same at 3 points.
Now we should say that you can use 3 jack screws, or there is actually a like a flat. What do you call it?
I use a leveling plate, a round
leveling
and sharp
plate, okay.
leveling plate. It has a fixed point and 2 knobs, and
Okay. Basically does the same
same
thing.
thing.
Yes.
So now, at each point, we read 0. So we've established a plane across that. So we check the whole plane, and we're looking for how much variation. That'll be the flatness.
So now you're just moving the dial indicator across the plate, looking for any variation.
Any
in the
variation.
needle.
All of a sudden, we come to a bad spot, and it goes up about 3.5 thousandths.
Okay.
That gets included in the flatness measurement. So we're flat basically to 3.5 thousandths on here. Now let me explain what happened with the viewer. The viewer that wrote in, somebody showed him a way to make better flatness measurements, and what had happened was, by accident, the part could be set up on one of the bad areas, the jack screw.
Meaning the jack screw is underneath a bad spot. Okay.
And let me show you. I'm going to go ahead and do that. I'm going to zero it on that area, even though we know that's higher.
Yeah,
I
so-
can still zero it on any 3 points. Remember, a plane is 3 points.
So we're assuming now somebody's given you this. So it's a fresh part. You're assuming it's flat. You set up your jack screws. It just so happens that you've put a jack screw underneath a bad area on this, but you don't know that yet.
You don't know that yet.
So you're zeroing it
So
out.
now we have 0 at that point, 0 at this point, and 0 at this point, because we didn't know. There was no piece of paper.
So you're going,
We just-
okay, I'm parallel.
I've
I'm
got,
good.
so let's measure the flatness on this part. Remember how the needle didn't move at all?
Okay, and now it's
moved down. How far did it go down?
about 3 or 4.
About 3.5, let's say. Okay, it keeps going. There's 3.5. And then it goes up past 0. Whoops, came off the part. About 1/1000th up. Oh boy, about 4.5 thousandths down. So it's showing about 5.5 thousandths flatness. You say, well, wait a minute, are we still 0? Yeah, I've got 0. Yeah, I've got, well, basically, I came off the plate a little bit here. Let me So yeah, I still have my
still
3
0,
points.
so what's going
What
on?
it was
Yeah.
is you were set up on you were giving a false plane to start with.
And the indication that you would have that maybe you did that is what?
The movement is very smooth and even here.
The variation you're seeing on the
Right,
dial
the
indicator.
needle movement. The needle movement's very smooth and even, but all of a sudden, when we went over that jack screw area, it jumps. It jumps from here to there. That's an indication you're on a bad place. That wouldn't be the right place to start your plane.
Okay.
You would want to have moved it over to here. So what it amounts to is he was shown you'd have to do this twice. Right. First was the unknown. Find what looks like the best 3 areas on that plate, because that'd be like the median plane.
Well, I guess that would be one way to do it, is just to do it twice.
Do it twice.
Do it twice. Take a measurement, then just move each jack screw
See if it improves.
a few degrees and do it again. Okay.
But after you measure it the first time, look and see what looks like good, smooth measurements.
Okay.
So that was how you can get a better flatness measurement using same 3-point method. What can happen if you choose the wrong plane to start?
All right. And you know, we have a viewer question, but before we get to that, just a reminder, any other questions, send them to techno-live@qualitydigest.com. We do have a few minutes. Why don't you happen to have it? Why don't you go ahead and show what the your leveling plate looks like, just so
I
people.
will. Let me bring that out.
So what Craig was showing was 3 jack screws, which is kind of I'd call that the poor man's leveling plate. Is that what you want to call it, Craig?
Yeah, that would be.
So as Craig's looking for an actual leveling plate here, just a reminder, send your questions to techno-live@qualitydigest.com.
Not coming up.
Craig's looking for his leveling plate.
Yeah, not coming up. What it is, it's a plate that has a very, very nicely machined surface, one solid point, and two knobs that have very fine pitch, so you can accurately adjust. Again, you'll move your indicator over 3 parts, and you just dial them in. It's very fast.
Okay.
It's a very fast method.
Let's get to one of our viewer questions that just came in a few minutes ago.
All
if
right.
we can pop that up on the screen there. During an audit check, we found that the gauges used were out of calibration, but well within the calibration date posted on the label. How do we deal with the components accepted with this instrument and used in the assembly line and dispatched to a site?
They have a problem.
They have a problem.
The calibration due date means nothing in this case. If they know the gauge is bad, those parts would have to be rechecked. It's a common occurrence. Somebody dropped the gauge, now parts are hanging off. It doesn't matter what the date on the calibration tag says, they would have to redo it.
Right.
Recheck.
And by the way, I believe, I'm not positive, but I believe it's a requirement if you're ISO 9001 registered that you actually have a process in place for if you have an instrument that is out of calibration and you have products out in the field, I believe you need a corrective and preventive action to go with that situation in terms what is now the disposition of any parts that are in stock that were inspected with that piece of out of calibration equipment, and what happens with any parts that are out in the field. So it is really critical. And I think probably at a minimum they would have to pull samples from the field
There's a number of things. Another thing would be the engineering requirements. A lot of times the engineers will put a much tighter tolerance on the part than is actually needed for the function. So you need to know how far out of tolerance it actually was. Your first step probably would be get that gauge to a calibration lab and get some before readings. Before they do any adjustment, get some readings. How is it measuring today? What was 1 inch measuring? Was it measuring just off 1,000th or was it off 30 thousandths?
Right.
Sometimes the engineering spec can handle that. They'll still need to analyze this, and I agree with you, they should pull samples.
Yeah.
But it might be one of those where their CAPA or their corrective action might just state it was well within the parameters of design.
Okay. We have another question that came in related to dial test indicators. How do we know what is the correct length of the probe? And let's take that question first.
Sure.
And we'll get to the other one.
How you know one indicator would be a good quality replacement tip. If you're buying a Brown and Sharp replacement tip, if you're buying from Brown and Sharp, they'll always ask you what model number. So the model number has a certain length. You can find it in the catalogs if you happen to have that. The Mitutoyo catalogs also, I know they'll show what contact points will work with what indicators, because sometimes they'll make them where they'll handle 2 or 3 different types of indicators.
Well, I hadn't thought about that. I mean, you could have a situation where maybe you haven't used one in a while, you go to the tool crib, you pull out a dial test indicator, and it doesn't have a tip on it.
It doesn't have a tip.
And you go, and you don't have the manual, you don't have anything on it, so yeah, your only choice is basically go to the manufacturer and...
Right.
I mean, it's not usually like scribed on the back or anything like that?
No,
Really?
the tips are too small.
I mean, on the back of the...
On the indicator, no, because
itself?
there's no serial numbers, there's no model numbers on the contact points.
Okay.
Look, probably the tool crib, if they had more than one, they probably have a little stack, and they would say this is for the Mitutoyo 503-102.
Okay.
And they would use those till they ordered new.
Okay.
But just because it threads in does not mean it'll work. The second part of that question was why would it show a different measurement? It's designed. I can
show you. This is really brief, but let me get a piece of paper here, and we'll sketch that out for you. Basically, it's just kind of basic trigonometry, and people are going to kind of dispute some of what I'm saying here, but it's close enough. So, okay. So this is your actual instrument, your indicator right here. You've got.
Make it a long one.
We've got a tip that comes off, except it's straighter than that, of course. You've got a tip that comes off. You deflect it a certain angle. Okay, so your tip started off here, you've moved it up to here. So you've got an angle right there. Trigonometry says that this distance is related to this angle and this length.
And this one.
I'm sorry, yeah, this angle and this length. So if this length gets, if we were to extend this, so let's say, and the dial indicator knows what this length is because it's designed for that. So it knows that when it has this much deflection, it's going to give a certain reading. Now let's just say you've extended this. Take that. Well, that also, when you move it, this is also going to be up here further. Now you draw this distance down, and that's where you're seeing that difference. This is what's known based on a certain deflection and a certain length. If this length is longer or shorter, then that is going to affect
the movement.
The movement, and this is, it's just basic trig, right? This distance is going to change based on the angle and the length.
And the length of the leg.
And so the angle's a given. The length is what you're changing. That's going to change this. That's going to change that distance right there. So that's kind of it in a nutshell. Close enough, anyway.
It is, and they're designed. You can't visually tell. It's not like you're going to look at the indicator and say, oh, that's the wrong tip, unless it's something drastic. You've got 20 of these indicators, you're used to seeing a certain length, and all of a sudden, they do make some, Interrapid makes some that are 5, 6, 7, 8 inches long. So you can have that where you visually know, but normally, it's just have it calibrated. If it's the wrong tip, the calibration lab, if it's a good calibration lab, they're going to pull the tip off and say, do not use.
Right.
Either they will offer you a replacement or tell you you need to get a new one.
Okay. We got another question. Put that up on the screen. For optical flat testing, is there a CMM or any other method that can be used to test flatness of the anvils?
Typically, the flatness of the anvils that we're looking at are, I'm guessing, yeah, a 0 to 1 OD micrometer would be 50 millionths. You could probably resolve that with CMM. They resolve down into the 10, 20 millionths. I don't know if your accuracy would be there. Optically, it's flat. With the CMM, it wouldn't be that fast.
Well, and also it'd be tough with something like a micrometer anvil. I think obviously if you're doing something larger,
yes.
then I think something like a CMM would make sure. I'm not sure about vision systems. I think what we're talking about here is when you're talking about a flatness of something that's fairly small, an optical flat, even though they're expensive pieces of glass, they are much less expensive than a CMM or
you can lug them out to the machine. Also, you can't move them.
Yeah, and there's other form measurement. A number of companies make form measurement devices. Who is it? German company.
Hummel.
Hummel, Zeiss, they make form measurement devices. But again, if all you're doing is some flatness measurement on some relatively small pieces of metal, I'm not sure it would make. Now, if he was talking about optical flats, something like what you were showing here, larger flat, then obviously, CMMs, even arms,
be a choice.
Portable arms.
I don't think the arms would be accurate enough, but I could be wrong there.
Okay.
I could be wrong.
Okay. Another question. If we throw that up. We would get this question. How do you determine gauge uncertainty? Well, I'm glad you asked us that. Can we
call a friend?
Can we call a friend? We probably should have done that. We're not experts on gauge uncertainty. You are fortunate in that if you click that little banner underneath our page, the folks over at PQ Systems are. Basically, I can kind of explain it briefly, and this won't be super accurate, but if you're just looking for a layman's explanation of how gauge uncertainty works, is you measure several different parts over and over again with the same operator and the same piece of equipment.
That's more gauge R and R.
Oh, that's gauge R and R.
Gauge uncertainty.
See, that's why you asked the wrong guy.
And I'm not the right person for that either, but I am familiar with it.
Okay.
Gauge uncertainty is more or less the tolerance within the gauge and some other factors. So there would be the tolerance, the inaccuracy of the tolerance. The user does come into play, but not for the gauge uncertainty.
Okay.
The gauge uncertainty is defined in its manufacture.
Okay. Yeah.
The way it's manufactured. But PQ Systems has some excellent modules that cover gauge uncertainty and gauge R&R, so you get both.
And actually, they actually have an expert on staff there who can completely refute everything that Craig and I just said, because we're not actually, and by the way, we are actually trying to get somebody on the show at some point who will actually give a demonstration of gauge measurement, gauge R&R, and actually go through it hopefully in some detail. And if that happens, we'll send out an email on that, and you guys will get that, and you'll get it straight from the horse's mouth. And that was all for questions. Anything else you wanted to cover today?
I think we've pretty well covered it.
All right. Well, once again, guys, thanks for showing up for our show. If you have any questions you think of once we sign off for the day, like I said, go ahead and still send them to techno-live@qualitydigest.com, and we will forward them on to Craig once we get them, and he will just answer you offline if he can. And if he can't answer the question, we have lots of experts among our users and so forth, and we can just forward it on to them, and we'll find somebody who will answer the question for you. So before we go, once again, I'd like to thank Mitutoyo for supplying us with some of today's equipment, and of course, to our sponsor, PQ Systems. For 30 years, PQ Systems has provided quality control software and training to help people in manufacturing, healthcare, government, and service organizations demonstrate proof of their quality performance. Visit www.pqsystems.com for a full range of products and services that PQ Systems offers. Or, once again, you can click that banner right underneath the player page, and it'll take you right out there. Craig, thanks again for coming out here.
Thank you for joining us.
Sharing your expertise with us today. And thanks to all of you for joining us. And we'll see you again at the next Gauging Quality. So long.